Okay, so let's work on this problem. We've got a man and a ladder leaning against the wall. The ladder doesn't fall over because the wall is holding it up and friction from the ground is keeping it from sliding down the wall. We see that the ladder has 180 newtons in weight, the man is 800 newtons in weight, and the ladder is making an angle 53 degrees with respect to the ground. The height of the ladder is 4 meters. And so we can do a quick calculation to figure out this is 4.0 meters and this is 53 degrees, then the length of the ladder must be 5 meters. We get that by taking 4 meters and dividing by the sine of 53 degrees. That must mean that this distance is the length times cosine of 53 degrees. This is 3.00 meters. Okay. On your sheet, I have it slightly miswritten. I mean to say that this guy is 1 meter over, not 1 meter up. Let's just make it a little bit easier. You could do it with 1 meter up. It'll change your answer a little bit. We'll do 1 meter over. Okay. We want the normal force on the wall, by the wall on the man. So we're going to start by adding forces to our diagram at each point. So our forces, clearly we've got the weight of the man, which is going to be pretty large. That's 800 newtons. So this is weight of the man, and that's right there. We also have the weight of the ladder. Weights of extended objects always act at the center of mass, which is at that point right there. This is going to be a much smaller weight, only 180 newtons. But this is the weight of the ladder. Then we've got the normal force acting on the ladder. We don't know how big that is yet. That's the whole point. Make that straighter, because it's pointing straight out from the wall. This is the normal force from the ladder, or by the wall, rather, on the ladder. And then we have the two forces by the ground. We have the normal force by the ground, which is pointing up, which should be equal in length to both of the weights added together, something like that, approximately. So this is the normal force by the ground. Make sure we give each force its own independent label. And then we also need the friction force. The friction force is going to end up being equal to the normal force by the wall. So this is a static friction force. Okay, so we're going to write down 3 equations for our statics problem here. We have the sum of the forces in the x direction is equal to 0. Sum of the forces in the y direction is equal to 0. And then the sum of torques is equal to 0. But we need a pivot point for our torques. So how do you choose a pivot point? You want to add a location where there are some forces that you don't care about, because you're going to be zeroing those forces out in the torque equation. We want to know about the normal force up here. So we don't want the pivot up there. We know the weights, so we don't want the pivots to be there. So we'll choose to put the pivot down here, because we don't know the friction force and we don't need to find it. Okay, so we'll write down our equations. Sum of the forces in the x direction. We have a friction force minus normal force by the wall is equal to 0. For the y direction, we've got a normal force by the ground minus the weight of the ladder minus the weight of the man is equal to 0. And for the torques, we've got 2 clockwise torques and 1 counterclockwise torque. We have the torque due to the wall minus the torque due to the ladder minus the torque due to the man. It's all equal to 0. Well, it's going to turn out that the torque equation might be enough for us to solve this problem. So let's focus on the torque equation first, and then we'll use the other 2 equations only if we have to. Okay? So, let's start filling in the torque equation. Now, the equation for a torque is either R times F times sine of the angle between the radial arm and the force, or R times F perpendicular, or F times R perpendicular. This time around, we'll see that F times R perpendicular is by far the easiest way to calculate this. But we'll show you in 2 different ways. For an example, let's look at the torque due to the man. Now this is going to be a clockwise torque, so let me put the minus sign here. Okay, if we were to do this with RF sine phi, this wouldn't be so terrible. What we would do here is we would go, here's our R, starting along here, we get to the force, and then we follow it along. Okay. So this is going to be our phi for the man. So that is clearly going to be phi sub m is going to be 90 minus 53, which is 37 degrees. Well, what is R? Well, we know this is 1 meter, so it's the hypotenuse that gives us an x of 1 meter. So R is equal to 1.00 meter divided by the cosine of 37 degrees. Not 37, sorry, 53 degrees. It's 1.6616 meters. I'm giving extra sig figs to make sure that everything fits in. Okay, so this is equal to negative 1.6616 meters times our force, which is the weight of the man. Notice we already have newtons, so that's just 800 newtons. We're not multiplying by g, this is already the weight. We're just done. Times sine of 37 degrees. If you multiply that all out, you get negative 1.6616 times 800 times sine of 37 degrees, you get negative 800 Newton meters. Huh. That's an interesting number. Because let's calculate this the other way. Let's calculate this with negative torque of the man is equal to negative RF times R perpendicular. What is R perpendicular? Let's go back up to our picture. R perpendicular is what you get if you follow along the force until you are perpendicularly across from the pivot point, and then you go across. So this distance right here is R perpendicular. Well, what is that equal to? That's 1 meter. So this is equal to negative 800 newtons times 1 meter. Negative 800 Newton meters. Boom, we're done. No dividing by cosine 53, no multiplying by sine 37, no finding angles. If you know R perpendicular, then you're just done. We can do that with the torque of the ladder as well. So what is R perpendicular for the ladder? Well, this is halfway across. So we follow the line of the force. It doesn't matter which way you go along the line of action of the force. You go either way until you are perpendicularly across from the force. And then perpendicularly across from the pivot, and that length from here to here, that is your R perpendicular. Well, what is it? Well, the whole length is 3 meters. This is half the length. So R perpendicular is 1.5 meters. This is equal to F R perpendicular, which is equal to minus the weight of the ladder times R perpendicular for the ladder, which is equal to negative 180 newtons times 1.5 meters. Negative 270 Newton meters. So our torque equation is the torque of the normal force by the wall minus torque of the man minus torque of the ladder. All that was equal to 0. Torque of the wall is equal to torque of the man plus torque of the ladder. All right. We've been doing these minus torques to remind ourselves that it's counterclockwise, but here we're adding these torques across. Well, what is torque of the wall? What is the equation for torque of the wall? Well, it's equal to the normal force by the wall times R perpendicular for the wall. That will be equal to the torque of the man plus torque of the ladder. Two things which we already know. We're trying to find the normal force of the wall. So if we can find R perpendicular for the wall, so this is going to be 800 Newton meters. Why positive 800? Because it was negative torque that was equal to the negative 800 plus 270 Newton meters divided by, well, what is R perpendicular for the wall? So let's be careful here. The normal force goes this way until it reaches here. This is perpendicular for the pivot. We come down here. So this is R perpendicular for the wall. So it's 4 meters. So the normal force by the wall is 267.5 meters. Newtons. 267.5 newtons.